Voltage regulation, again, as I mentioned, these are interrelated topics: voltage regulation, voltage drop, power factor. I thought I clearly answered this question. Maybe the student didn't get a chance because I uploaded the live training recordings a little bit late. Um, Maybe that's the reason. So it's saying that using the equation VR percentage, do you use 0.05 or 5%? And do you put 200 at the end under everything in the parentheses, or just the squared portion? So I understand that this particular formula, this particular equation causes a lot of issues for students. And in the live training, those of you who have gone through this, I was pretty explicit about how we handle it, right? So the general consensus, my recommendation that will help you save time and avoid mistakes, is that carry the percentage sign as it is in the VR calculation. In fact, if I remember correctly, I said that treat the percentage sign as a unit of measurement, correct? Did I say that? I remember saying something like that, right? Imagine that this is 5 kilo ohms. Okay, like carry the percentage sign as a unit of measurement, and it will basically just work its way through. All right. And highlighted term is going to be insignificant. That's what essentially the student is indirectly asking. So it will be insignificant. And yeah, it's a factor within the outer bracket that needs to be calculated on its own and then added to the remainder here. Okay, guys. All right. Voltage regulation. As I mentioned, voltage regulation, voltage drop, power factor. These are all interrelated concepts. So this is a fairly open-ended question that I received from student, and I'm going to take a stab at this. We've discussed this in quite a bit of depth in the live training as well, and feel free to ask me any questions that you might have while I'm going through this explanation. Let's go through the question first. In my voltage regulation, in the voltage regulation equation, you have mentioned VSNL, secondary no load voltage, is the same as VP by N. And guys, when I'm reading these statements, sometimes I'm adding the, just because in my mind, I would like to read it properly, right? But yeah, it's not that I'm seeing something that you guys are not seeing, okay? So the question is that I mentioned VSNL is the same as VP by N. My question is, how am I supposed to get VP? Okay. VP should be no load primary side voltage. He's right. He's already answered the question here. But transformer nameplate voltage is full load rated voltage. Okay. So the rated voltage applies at the terminals, at the output. That's what he's saying. Okay. Because the rated voltage takes into consideration the voltage drop. So that's the angle he's thinking through. In my mind, VP by N is not correct representation of VSNL. Okay. Let me know your thoughts. What do you guys think? I think the student is confusing two different concepts. Okay. And he partially answered the question himself. Yeah, the way the question is asked, it's confusing. So there are two aspects to this. I think an easy way to start this is by looking at our ideal transformer. I apply a primary voltage. We have turns N, P, and S. Turns ratio is A. I get VS. You guys agree with me that VP by VS is equal to A, correct? Which means that VP by A is equal to VS. So far, so good. Any issues here? This is called learning things from first principles. Okay. Take a step back, go back to square one, and start working through there. Any issues here? No issues. I said that this is ideal transformer. What would that mean? That VP, no load voltage, will be equal to VP, full load voltage, Vs no load is equal to Vs full load, because we don't have any of this stuff. Any of the non-idealities, no losses. Okay. All right. Now let's take a look at the scenario where the input voltage, guys, that we are applying, right? I'm applying an input voltage, correct? Vp. And then I'm getting an output voltage Vs. Now let us assume that this is no longer an ideal transformer. This is a non-ideal transformer, correct? Now in a non-ideal transformer, and again, I'm trying to explain these things from first principles. And for that, I'll have to now sketch the equivalent circuit of a non-ideal transformer. What does that look like? On the primary side, I have Rp, I have Xp. Make sense? You guys agree that, and we did discuss it, in most of the equivalent circuits, we show the core parameters on primary, right? Rc, and then I have what? X, M. Cool. And then on the secondary, I show my RS, and then I show my XS. Cool. So far, so good, guys. Right? Now, if you look at the initial, like intermediate step, we actually show an ideal transformer here. Correct? You guys remember that? Okay. So I have incorporated the non-idealities, right? And then I obviously have to have some sort of a voltage transformation, right? You have number of turns on the primary, and you have number of turns on the secondary. And in most of the textbooks, you're going to see that they show something like this to emphasize that this is an ideal network. Correct? Okay. Now, here is the punchline. Here is a punchline. This is primary. And this is secondary. So far, so good? Right? And the turns ratio NP by NS is equal to A. Yeah. Now, if I want to move this block, okay, let's start with the simpler stuff actually. Forget about the block. If I want to move this guy over to here, what will be the value? How can I move just this parameter over there? The formula that we use is that Zp is equal to A square Zs. You guys remember? So this primary impedance, if I want to convert it onto the secondary, it's going to be Zp divided by A square. Not Rp by A, there's a square. When we're dealing with resistance impedance, it's square. When we're dealing with the voltages or current, it's a simple A. So if I were to move this block over to the right-hand side, it will show up as another resistor on the right-hand side on the secondary with the value of Rp divided by A square, and another inductor over here with the value of Xp divided by A square. You guys agree? Make sense? So when I'm looking at the series parameters, do you guys agree that this would be equal to this on the secondary? What do I have collected on what have I collected on the secondary? I have series resistance in the form of Rs plus Rp divided by A square. Correct? I have collected these reactances xp by A square plus xs. Correct? So far, so good. So this no longer exists over here. I have moved it to the secondary. So notice what I mentioned in this diagram. Equivalent circuit referred to the secondary. Okay. Any issues so far, guys? I'm taking baby steps as always. First principle. Okay, you don't need to memorize anything. You don't need to sort of know rocket science. It's just unbroken chain of logical thinking. That's it. Nothing fancy. Now, if I were to move this block to the right-hand side, can I do that by simply doing RC by A square, XM by A square, keeping them in parallel? They're in parallel. They're going to end up on the secondary in parallel. All I have to rescale, readjust, recalibrate are their magnitudes by dividing them by A square, just like we did. We're just simply sticking with this formula. And that will also bring them here. Yeah? Right? So I've moved the parallel block to the right. Now the equivalent emphasizes that there is a Rs plus Rp by A square component and Xs plus Xp by A square component. You guys are good with this? You guys are good with this? What about the input voltage? Okay. What about the input voltage? Now, here is the catch, guys. Here is the catch. So if I have moved these parameters over, please pay attention to this carefully. Now, let me redraw this. Okay, I have this habit of just scribbling and scribbling and scribbling and scribbling, but since I already have a diagram in front of me, I'll hopefully do a better job now. So what I'm left with is this ideal transformer. I have moved over. Now you can argue that, okay, Wasim, the series parameters are gonna appear first or the parallel block is gonna appear first. How did we address this question? Actually, let me draw it and then it will make sense for you. It probably does already, but so should I do this on the secondary? This is R equivalent, X equivalent. This is RC by A square. This is XM by A square, right? And you can throw a J, whatever, it doesn't matter. Okay. It does matter in as to how you handle it later on in the formulas and equations, but yeah, you get my point. Or should I show it like this? Should I bring it before 1 or 2? Should I bring it before the series parameters or after the series parameters? And actually, the reference handbook answers this question. If I move it before, which is 1, number 1, what is the equivalent circuit called? That type of equivalent circuit. What is it called? It is called the approximate equivalent circuit, right? Because the way we started out our original circuit, you remember that we had the series parameters on the primary side upfront, yeah? And then we had the parallel component. So if you do a mirror image or you move the components over, then you should have, from the standpoint of the circuit on the secondary as well, that same stuff happening. But anyways, regardless of what is happening over here, we're going to keep it like this. It's insignificant, as Chris is saying, there's 1 to 2% difference in voltage. Now, everything has been moved from primary to secondary. Whatever voltage I apply here is called VP, isn't it? And that's my primary voltage. This is a punchline, guys. I mean, this is the stage that I was setting everything for. With the turns ratio A, what am I going to see on the secondary? So VP divided by VS is equal to A. So VS is equal to VP divided by A. On these terminals, the voltage that I'm going to see is VP divided by A. Clear? That's where VP divided by A is coming from. We are not done yet. We are almost there. Now I'm going to tackle the question that the student asked head on. Okay. So these terminals that you see are actually on the secondary of the transformer, of the ideal transformer. All the non-idealities have been shifted over to the secondary. And this is what the voltage is. VP by A is appearing over here. So in my mind, VP by N or VP by A is using N is not correct representation of VSNL. Let's see. What is VSNL? Secondary no load voltage. If I don't have any load connected over here, and if I want to make this VS into VSNL, what has to happen? There should not be any current flowing, correct? If there is no current flowing, these terminals are open, let's say. There's no voltage drop here. This VP by A is appearing across this guy. And the voltage, can you guys now see that VSNL and VP by A are the same thing? Okay. So this is a long story that I've told you in order to answer a fairly straightforward concept. But the key point is not in the answer, it is the approach. First principle, unbroken chain of logic. Baby steps. Okay. And that is the habit that you guys have to develop while dealing with these questions. So over here, as I told you, the student sort of answered his own question, but you can see that there's a lot going through his mind. And I think one of the comments that you guys mentioned after reading the question was that I'm confused. Okay. Because if someone is not clear in their own thinking as to what they're asking, I mean, that's so have a laser focus on even the question that you yourself are asking, because a lot of times the answer is in there. And he did sort of allude to that. All right, guys. And yeah, as far as the equivalent and the approximate is concerned, if we bring the and this is something that shows up in induction machines as well. If we bring the parallel parameters, the core parameters, close to the source of the voltage, it's considered approximate. Because the easy thing is that what it helps us with is that we can then apply the voltage directly across the series arrangement as well as a parallel arrangement. If you look at it as a block, and I think this is how I explained it, right? This is the parallel component. Let's say we have a source voltage, correct? So this is the series parameters, your RP and R equivalent and X equivalent. And this is a parallel containing RC and XM, correct? Now, the exact, or there's no such thing as exact because these are still approximations. Arrangement would basically show you, the exact arrangement would show you the series components first and then the parallel after that. But by bringing the parallel ahead of the series, this voltage, let's call it V, is applied directly across the parallel component. And that makes our job easier because whatever the load is and the terminal, then this V is being applied to the parallel component as well as the series and the load. That is basically the idea behind here. Okay. All right. I hope that you found this helpful, and please take this approach in solving every question. All right. So one problem where we have two Y loads and one delta load. If we are using V phase, do we need to worry about 30-degree phase shift because the handbook is not providing any information? If you have two Y loads and one delta load, you're going to use V phase. It's very abstract on what you're asking. So if I sketch it on a block diagram, and again, the discussion for voltage regulation has ended over here. I'm just taking a question on the question number 8 from where? 8.3J. Let's take it offline on. Actually, better yet, can you submit that question on the community? Right? If you can submit that question on the community, you're going to get fast response. So full load voltage is less than VPA. Yeah, of course. The full load voltage is what is appearing at the terminals, right? The nameplate discussion that the student sort of started thinking about, he started confusing no load and full load. And that's where he went off track. We have a couple of other problems that we need to tackle as well, guys. So I would like to move away from it. But this, the nameplate thing that he sort of inserted in it, it sort of muddied the waters. Okay. Yeah, he connected the VP to nameplate. Okay, let's move on. We have a few other questions. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE Electrical and PE Power Exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE Electrical and PE Power Exam preparation programs, please visit my website, studyforfe.com.